So there has not been any more deaths from COVID in the county. Good. Hospitalization numbers, there's 17 people in the hospital, 2 people in ICU. Those numbers went down since last time I seen you as well. Additionally, the vaccine numbers, it keeps increasing. Good. Let's check out the daily positive numbers of COVID. So people that were diagnosed with COVID in the county. You're checking out this curve from a far distance, from a zoomed out distance, and you're noticing, doesn't look that crazy over here. It looks relatively flat still. If we zoom in on it, let's see those numbers. So what happened here? The 13th, we had 46 cases. The day before that, there was 50. The day before that, there was 38. The day before that, there was 22 on the 10th. Then you also had 49 and 46. So yeah, we're definitely inconsistent here with the number of cases. Maybe this is the effect of Easter still, or getting together over spring break of a holiday. So those numbers, not the best, but not something that we haven't seen before. Not like beginning of the year. So again, yeah, we wanted them below 40, we wanted them below 30, want nothing, but they're not too crazy. All right, so there's the COVID report for today. Definitely still out there. Protect yourself, protect your loved ones. That's why I'm wearing a mask. That's why school is so much different. Our lives are so much different. Obviously, so be smart, be safe. Protect yourselves, protect your loved ones. Let's figure out what's happening for the best class of the day. So here we go. Welcome back. Quote of the week comes from J.P. Morgan. The first step towards getting somewhere is to decide you're not going to stay where you are. Set some goals in life. Reach those goals. Set some bigger goals in life. Reach those goals. Keep making your life a little bit better. So figure out where you want to go and get there. Today's Thursday, April 15th, 2021. Today's a day 4. We are continuing on with unit number 8, which is oxidation and reduction. We're going to finish up half reactions today. You'll have an exit pass. It'll be due on Saturday. We'll finish up the examples on half reactions. We'll give you some time to work on the exit pass. And then we'll jump into Voltaic cells. We'll introduce Voltaic cells. I'll start off with a demonstration. We'll get into some guided notes, and I probably will not get through 4, 5, or 6 today. We'll probably say 4, 5, and 6, task 4, 5, and 6 for next class. But we'll probably get that video next time. But that resource is there. If you want to watch it today, we'll watch it tomorrow as well. You have a reference table below. You have the video below too. Does anybody have any questions for me before we start today's class? Just so you know, I do have a couple people in class, so we'll be interacting a little bit different than what we're used to. But I won't forget about you guys at home. 23 of you guys at home, I'm still here for you. All right, on the agenda, first things first, we started off with the examples, topic 3. Please open up the agenda. Please open up the examples on Google Forms. It's above. Maybe you want to open up your guided notes to assist you as well. So we did start this last time. Let's open up our guided notes to do a split screen. So open up your guided notes. Here they are. Get them ready for us. And I'm going to scroll down to half reactions. So topic number 3, half reactions. Right here. So again, refresher, what we talked about with oxidation, reduction, half reactions. Let's just scroll through it. Reduction, half reaction. What you should know, reduction, half reaction, GER, gain of electrons is a reduction. For reduction, half reaction, it's going to be gaining 1 or more electron, and the oxidation number is reduced. The oxidation number is going down. You're gaining a negative charge. You take a negative charge on, it's going to become more negative. So again, the oxidation numbers are reduced. I know it's tough to see there, but these oxidation numbers are going to get reduced. Another thing you should know is the placement of the electrons. For reduction half reactions, the electrons go on the reactant side. So the reactant side's to the left. Reactant side, there's the placement of the electrons. Always is set up with electrons to the left. For oxidation half reaction, very similar, but the placement of electrons is a little bit different. Oxidation we know is Leo. Oxidation, loss of electrons is oxidation. It's losing one or more electrons. Its oxidation number is going to increase. Oxidation number increases. So this is an oxidation number, goes from 0 to +3. I know it's really faint to see. 0 to +3, its oxidation number is going to be increasing. If you're losing electron, think about it. If I have an electron just hanging out my shoulder, electron's negative. If I take a negative charge away, I become more positive. Get rid of those electrons. Get rid of that negativity in your life, become more positive. That's what you want to do. Lose those electrons. The placement of the electrons goes on the product side. So another thing, the placement of my electrons is definitely different than the one above. We talked about half reactions. We're going to use that quite a bit for the rest of these questions. We did some of these. I don't know exactly how far we got. I think we got through at least 4. Does anybody recall what number we left off on? Do you guys remember? Remember we left off with the examples? Anybody at home remember what number we left off on? If we don't, then I'm just going to start at number 5. It's been a couple days. I should have wrote it down, but we finished number 3. All right, thank you. We're going to start off with number 4. So every classmate said, I think 4. I'm going with 4 too. If we already did it, no big deal. So here we go. Question number 4. Thank you very much. Says, which half reaction correctly represents reduction? So again, I'm going to keep working on the process of we do them together, or I'll guide you through them. By the time we're done with this, you should be able to do the exit pass on your own. So here we go. Which half reaction represents reduction? I'm going to use my guided notes. Let's go through it. We're looking at reduction. Reduction is referring to this segment of our notes. It's gaining an electron. The placement of my electrons is going to be on the reactant side. Electrons are on the reactant side. So first things first, I'm going to look at the placement of the electrons. If it's not on the reactant side, it's not going to be the right format. So again, reactants, chemical reactions go from reactants to the product. Reactants on the left. Electrons must be on the reactant side. Choice A, the electrons are on the reactant side. That looks okay. Maybe it's that answer. Choice B, the electrons are on the product side. Hopefully you can see that's the product side of the equation. No, can't be that answer. Can't be B. Choice C, the electrons are on the reactant side. That's the reactant portion of the chemical equation. So that's reactant. Maybe it's that answer. Choice D, the electrons are on the product side. No, it's got to be on the reactant side, so it cannot be choice D. Just by looking at the placement of the electrons, knowing the placement of electrons, we got rid of choice B, we got rid of choice D. You can see that electrons are on the product side, electrons are on the product side. That's not true. We're looking for reduction. The electrons must be on the reactant side, RR, reactant side. All right, let's go through this process. Next step, we have a better chance to get this right now. We have S minus 2, S minus 2, so minus 2 to S 0. So it goes from minus 2 to 0. What's going on from minus 2 to 0? Are we gaining electrons or losing electrons? Yeah. Examples do not have to be turned in, Tristan. let's see. So a couple different answers. -2 to 0. Think about this process. A -2 to 0. So it's going from negative to kind of more positive. So it's a negative to a 0. It's a negative to 0. So we're working on getting more positive. Maybe you want to do a number line. Okay, -2, -1, 0, 1, 2. We're going from -2 to 0. We're getting more positive. This situation, from -2 to 0, we have to lose some electrons. So electrons are negative. If I got rid of 2 electrons, I'm going to become more positive. This situation, the oxidation number goes from negative to positive. Oxidation number is going to increase. Oxidation number increases there. It gets bigger. Hopefully you can see that. It's getting bigger. That would be a situation for a LEO, loss of electrons. Doesn't look like it's going to be choice C. Let's try the last one. Let's check out. Doesn't look like it's choice A. Let's check out choice C. Choice C goes from +7 to +4. +7 to +4. You could analyze those numbers from +7 to +4. You know that number is getting smaller. So it's definitely getting smaller. For reduction half reaction, it says oxidation numbers are reduced or decreased. Those oxidation numbers are decreased. You see that the number is getting smaller. The charge is getting smaller. The overall charge of the ion is getting smaller. Why? It's got to get a negative charge. It's got to take a negative charge. Take another negative charge. Take another negative charge. If it takes more negative charges in, takes more electrons on, it's going to get smaller. Electrons are negative. If I gain some electrons, if I gain electrons, it's going to become more negative. From +7 to +4, it's getting more negative. Best answer for number 4 would be choice C. So first thing, figure out the placement of electrons. Next, think about the process of the oxidation numbers. Is it increasing? Is it decreasing? And that will help you out. 4, best answer is C. Let's try another one. Number 5. As S-2 ion is oxidized to S0 atom, the number of protons in the nucleus does what? So we're analyzing sulfur. We'll pull up sulfur on the reference table. So again, hopefully you guys at home are doing exactly what I'm doing. Hopefully you're thinking about the process. As I pose these questions, hopefully you're thinking about answering these questions at least in your head. Or you could always throw in the chat too. But sulfur, checking out sulfur. Element number 16. All right, there's the sulfur. How many protons does sulfur have, anybody? How many protons does sulfur have? Thanks, Alex. Yeah. Protons, sulfur has 16 protons. The atomic number equals the proton number for sulfur. Atomic number equals proton number for sulfur. Hey, Joey, please try to get here a little earlier, quite a bit earlier. Maybe you had an appointment, but welcome. All right, so yeah, so proton number equals the atomic number for sulfur. There's 16 protons. How about for the ion of sulfur? How many protons does sulfur have? So sulfur, I'm analyzing it from the atom to the ion. How many protons do I now have? So the first thing that Alex gave me was the atom. Sulfur 0 has 16 protons. That equals my proton number. For the ion, all that is going to be that -2 charge, referring to -2. S -2 is -2. What's that mean? It's going to actually add 2 more electrons. -2 means you add 2 more. So the Lewis dot diagram or electron configuration goes from 286 as the atom, electrons, 286, to 288. Those are electrons. So electrons change. What happens to protons? Protons don't change. If I lost some protons, it's going to be a totally different atom. So protons are not going to change. Protons is still going to remain 16. The electrons change, like him. Electrons change, but the proton number remains the same. So an atom of an element has the same number of protons. Like Kim, please try to get here a few minutes earlier for next time. So proton number remains the same. That should have been an easier question. S -2 to S0, number of protons, same. If I say check out element number 16, it's always going to be sulfur. It's always going to have 16 protons. If it's an atom, if it's an ion, it's still going to have 16 protons. 5 best answer is choice C. Number 6. I think you can handle this one. Which is true with Sn plus 2 ion is reduced? Think about it. Please put the answer in the chat for number 6. Reduced. Please record your answer in the chat. Hopefully, no reduced. Reduced. Oh, 4 for 4. Reduced. 5 for 5. Awesome. So reduced means reduction, reduced, gaining of electrons, reduction. Oh, it's that easy. Reduce, reduction, it gains electrons. Sn plus 2 ion is reduced. Think of gaining of electrons. Choice B is the best answer for number 6. Easy one. 6, choice B is the best answer. Next up, number 7. Let's try this one out. Take a minute or two. We're looking for the correct half reaction for reduction. Please try it out. Once you have your answer for number 7, please record it in the chat. Yeah, I know I'm muted, guy. I'm letting you guys try to think this out. I'm just working with a couple people in class right now. Thank you, though. Okay, please record your answer in the chat. B's and C's, B's and C's. Mostly everybody put B, but there's a C in answer, so we'll check it out as well. All right, check it out. We got rid of choice A. We got rid of choice D from the get-go. Why? Because the placement of my electrons. You should know reduction, the placement of the electrons should go on the reactant side. Reduction, electrons go on the reactant side. We should know, again, reactant is the first part of the equation. Yields, the product. Reactant, the product. Reduction, electrons go on the reactant side. So electrons have to go on the left side. It's not choice A, because electrons are on the right, the product side. It's not choice D, electrons are on the product side as well. It's not A or D. Could be choice B because electrons are on the reactant. It could be choice C because electrons are on the reactant as well. Now we have to figure out oxidation numbers. Let's check out some oxidation numbers. Let's see what happens here. Choice B. What happens in choice B? It goes from Ca plus 2 to Ca 0. So Ca plus 2 to Ca 0. What's going on there from Ca plus 2 to Ca 0? Plus 2 to 0. Think about it. Oxidation number is getting smaller. It's going from positive 2 to like a negative. How would it go from a positive to a negative? It's going to have to take a negative charge, take another negative charge, and gain up. In this situation, the oxidation number is reduced. That is reduced there. Positive 2 to 0. It's being reduced. It's getting smaller. Since it's being reduced, that looks like it's going to be a solid choice. Choice B is the best answer for number 7. Choice C goes from negative to more of a positive. That would be like losing in electrons. Leo. 7, the best answer is going to be choice B. 7 is B. Next up, try number 8, please. Reduction, half reaction. Think about the process. Do what we just did there. Take a minute. Please record your answer in the chat once you have an answer. All right, analyzing that question. Hopefully you saw what I just did there while I was on mute. I looked at the electrons, the placement of the electrons. I noticed that all my electrons were on the reactant side. So this time I couldn't get rid of any choices. All the electrons were on the reactant side. Okay. Next up, I went through and figured out which one's reduction, which one's oxidation numbers are reduced. I looked at choice A, it goes from 0 to +2. That's increasing. Increase is not reduced. No, can't be choice A. Choice B is going from 0 to +1. That's increasing. That's why I did an upward arrow. 0 to +1 is increasing, cannot be reduced. No. B, same thing, going from 0 to plus, that's increasing as well. No, can't be that. Choice D is going from 0 to -1. That's decreasing. That's being reduced. 8, the best answer will be choice D. Any questions for me, folks, on what we did there or how we got that? Any questions? Good? All right, let's move on forward. Last question here, I believe. Number 9. Take a minute to do this one. Please record your answer in the chat for number 9 once you have an answer. Number 9, please do it. Try it out. Please record your answer in the chat for number 9 once you have an answer. Oxidized. 26 people on. I'll wait for 6 responses and then we'll move forward. Oh, we're rolling in. I didn't scroll down. Thank you. Thanks, Crisscross. Thanks, Irvin. Thanks, Tintin. Thanks, Alex. 2 more responses. Oh, actually, there's one. Thanks, John. I think that's the same one. Thanks, T. Oh, we're good. A lot of responses. Thank you very much. So Leo. So oxidation, I think of Leo. Loss of electrons, oxidation. Leo, loss of electrons. It can't be choice C. It can't be choice D. Loss of electrons. How many electrons? 2. 2 electrons will be lost there. 9, the best answer is going to be choice A. All right, that one should have been an easy question too. So that right there, you could submit. You don't have to. I do not grade the examples. I do grade the exit passes. So we're all done with the examples. Let's shift gears. You could close that out. I don't grade it. Let's move forward. I'll give you some time to work on the exit pass for half reactions. So please open up the exit pass. If you paid attention to the examples, you know how to do the exit passes. If you pay attention to notes, you know how to do these exit pass questions as well. So please open up the exit pass. This exit pass is very similar to the examples. 8 questions. I'm going to give you some time right now in class to work on these 8 questions. If you have any questions for me, need help with something, please feel free to ask for help. I'm going to put you in a breakout room by yourself. Just in the event you have any questions, I will definitely help you independently. Please join your breakout room. Please ask any questions you may have. I'm here for you. So again, I'm giving you 10 minutes to work on this. At 12:27, we'll come back together. So you have from now till 12/27 to work on this. Please do so. If you don't finish it, it's due on Saturday. Please work on the exit pass topic number 3, half reactions. Please join the breakout room. Please complete this. Please join your breakout room. Please complete the exit pass, Unit 8, half reactions. Please join the breakout room. Please complete Unit 8, exit pass, half reactions. Hey, Joey, please join the breakout room. Santino, please join the breakout room. Let me know if you have any questions. Okay, guys, please make sure you turn in your exit pass. That's definitely gonna be graded. I'm in the process of switching computers so I can do my demonstration. There I am. Oh, cool. All right. So I think you could see this little, let's see, Almo version. Now I'm gonna figure it out quick. So you may want to pin J.E. Brown. I'm gonna do a demonstration right there. No, it's not appearing on that one. I'm just trying to figure out a different technology here, make it easier for you. So you continue to work on the exit pass so I really get this the way I want it, and then we'll begin. Oh, that's why. I'm gonna do my demonstration up there. Okay, please let me know at home if you cannot see this little image of my elbow or my hand underneath. I think you should be able to see that. It should be under J.E. Brown. There's a bigger image. We see this at home? We good? All right, so what I'm going to do now, I'm going to talk about a Voltaic cell. We'll make a Voltaic cell. I apologize if there's an echo in here, but with the Voltaic cell is the next topic. So we'll get the next topic right now in class. So to introduce this, I'm going to actually do a demonstration of making a Voltaic cell. Thank you. So the Voltaic cell, I know you can't see my face right now. The Voltaic cell is a battery. And what I'm going to do now, I am going to make a battery. I am going to do it a little bit different. I'm not going to talk about anything I'm doing at all. I'll tell you what I'm using. I'm using some water. I'm going to use some table salts, which I'll zoom out in a second. I'll use some beakers, clean beakers. I'll use a paper towel, and I will use an electrode as well. So you'll see all this material that I'm using right now. Again, I am making a Voltaic cell. I am not going to talk. I want you to observe, think about what I'm using, how I'm using it, and then we'll talk about the end. Enjoy the little show. All right, so I made a battery. There's one situation of a battery. What happened in this demonstration? I started off with, before I talk about it, what questions do you have for me? What questions do you have? I'm ready for a couple questions. Throw in the chat, unmute, whatever you want to do. Someone in class asked, why was it smoking like that? Was it smoking? No, it was actually inside there. We had a little chemical reaction. It is still doing that like smoke effect. It's a chemical reaction. In that situation, something's being oxidized, something's being reduced. So the more active a metal is, like it's still going on right now, but it's not as present. Let me zoom in on it again. So you guys did catch that when I tried to show you there. So it is still reacting, but it's not as reactive. There's some bubbling going on there. So that's going to be the losing and gaining electrons. So in this situation, something's losing electrons, something gains electrons. It's not fizzing as much. But that's proof that it's a chemical reaction. You can see it there. So why is it fizzing? Because you have a chemical reaction going on. It's a redox reaction. Thanks, Tristan. What other questions do you have for me? No more questions? You all could tell me exactly what I did there, why I did it. Let's try something else here. If I take something away, let's just look at numbers. 0.57. Take this away. Whoa, down to close to 0. I know there's a reflection there. But this is millivolts, just so you know. Really small. If I put that paper towel back in, let's check what happens again. Wet paper towel. Now we're back to volts. So there's a reflection there again. But yeah, we're back to volts. 0.55 volts. Take that paper towel away. What happened? Close to 0 for a second, and then we're at millivolts, really small values. Put that paper towel in. This thing's called the salt bridge. A salt bridge is going to be an aqueous solution. It's going to be a porous solution. It allows things to flow back and forth, ions to flow back and forth. What's the orange thing you plugged it into? That's called a voltmeter. This voltmeter tells you the voltage or current within the system. So this tells you how much voltage is produced with this battery. If I connected it to maybe a 9-volt battery, it should read 9 volts. If I plug it into the outlet, which don't do this at home unless you know about electricity, if I push this into the outlet, my prongs into the outlet with a positive and negative, it should read 120 volts. Don't do that. Another question somebody asked is also, why did you dye the water yellow? Just so you could see the water a little bit better. You should have noticed I did put table salt in the water initially. I wanted to make an electrolytic solution. If I did not put the table salt in the solution initially, then you would not have this voltage. Electricity cannot flow through a non-electrolytic solution. What other questions? Some good questions. Thank you, T. Anybody else? Right now, it looks like we're steady at 0.56 volts. This is copper. This was the another electrode of magnesium. Pull it out, you get close to 0 volts. If I switch up the electrodes, this is zinc and copper, it will give you a different voltage. Different metals produce different potentials, voltage. Like 0.8 volts, copper, zinc. My magnesium is pretty much corroded. I don't have any more magnesium, newer pieces of magnesium. Let me put the magnesium back in it again. But initially, when I put it in, it reacted really quickly. So 0.6 volts. The lead, when I put it in there, you could mix and match the combinations, but the lead didn't do too much. Millivolts, that's MV, millivolts. So it's obviously smaller than a volt. Yeah, you can switch up all sorts of combinations. Usually the magnesium, copper give us the pretty big potential difference. If you get lost on an island with your cell phone dies, and you don't have your charger with you, you can make a battery and charge your phone. Make one more phone call for help. That is a battery. That will produce electricity to charge your phone. How will you charge it? If you have a penny in your pocket, if you have a nickel in your pocket, nickel and penny, you take some saltwater solution from the ocean, put it into two different chambers, two different areas, two different buckets. You could come up with a salt bridge somehow. You take your earbuds that are connected to your cell phone. If you strip the earbuds from your cell phone, there's a copper wire there. It's going to take a little bit of creativity to really charge it. You will have a battery. All right, so that's my demonstration. Let's get into it. This is a Voltaic cell. We will talk about the components of making a Voltaic cell from here to the end of class. Give me 1 minute. Anybody have any more questions before I switch gears? Somebody asked how do the metals correlate with each other, and when you remove each metal, it loses charge. They're not transferring electricity. It's not a full circuit anymore. So when I took the metal out or took the salt bridge out in this situation, I broke the circuit. The circuit was no longer a complete circuit anymore. So again, someone noticed that if I pulled the metal out, it went close to zero. Close to zero. There's this one. Pull the metal out, it's close to zero. Millivolts are really small values. When I put it back in, you're going to notice you're going to get a voltage again. So when I take a metal out, it's going to break the circuit. It's not a complete circuit anymore. If I took the salt bridge out, it's no longer a complete circuit anymore. So electrons are not able to flow back and forth, or ions are not able to distribute back and forth to close that circuit. Good questions. All right, let's go through the guided notes, take some notes on Voltaic cells, and move on forward. All right, I think we're back in action. All right, so that's the Voltaic cell. Like that little diagram behind me, that's exactly what I just did there. I took a couple beakers, I took a salt bridge, a thing in the middle. I took two different electrodes, and I took that yellow thing called the voltmeter to make energy, to create energy. So that's the next topic we're on. We talked about a lot of stuff. We talked about signing oxidation numbers, done. We talked about redox reactions, done. We just finished up half reactions, exit paths, done. Now we're going to talk about topic number 4, which is Voltaic cells. So please open up your guided notes. Let's take some notes on Voltaic cells. If you understood everything that's going on with that reaction, you're in good shape. So my diagrams I have at the top of my sheet, I have a Voltaic cell. Right there is one of them. And then this one's going to be an electrolytic cell. So I have two types of cells there. We're focusing on topic number 4, this Voltaic cell, very similar to what I just did in class. So I only have like 10 more minutes of class. Let's see what we get done in 10 minutes. So topic number 4, voltaic cells. I'm gonna put this on a new piece of paper. All right, again, I will bold, I will highlight, just so you guys could differentiate between my notes and the text here. Topic number 4, voltaic cells, electrochemical cells. In a redox reaction, there are chemical reactions between particles being oxidized and particles being reduced. So what I'm gonna do first, I'm gonna get rid of a couple things, reactions. I'm gonna get rid of this section right here, it's a little typo. Between particles being oxidized and reduced. So oxidize and reduce. Again, I'm gonna bold, I'm gonna highlight. So redox reactions, we know there's something gonna be oxidized. We know something's gonna be reduced. An electrochemical cell involves a chemical reaction. Involves a chemical reaction and the flow of electrons. So what happened there? I took two chemicals, I took two different metals, I reacted them to produce electricity, the flow of electrons. Flow of electrons. Good old electricity. Allows you guys to use your Chromebooks. It allows you to have a connection for internet in your house. We took chemicals, reacted them to make electricity. There's two types of electrochemical cells. The first one we're going to talk about is topic number 4. It's a voltaic cell. And we'll really explore that voltaic cell inside and out today and next class. Well, mainly next class. In a voltaic cell, it's going to be an electrochemical cell in which it happens spontaneously. Electrochemical cell in which a spontaneous chemical reaction spontaneous means it's going to happen automatically. If you bring all the parts, if you have all the parts for this chemical reaction, it's going to have a chemical reaction and produce electricity. Happens spontaneously in a chemical reaction to produce a flow of electrons. Flow of electrons. Create energy. Electrical energy. So if you remember, I started off the entire unit. Under the Elmo said, tell me something you know about a battery. I had a battery under there. I had you guys thinking. I said, hey, how does the battery work? You thought about it. Some of you guys talked about a positive charge, negative charge. Some of you guys talked about energy. We'll definitely analyze that a lot more. The other type of electrochemical cell is going to be electrolytic cell. Electrolytic. An electrolytic cell is going to be like plating something. So metal plating something. Maybe it's copper plating. Maybe it's gold plating. Maybe it's silver plating. So a lot of times they do this in jewelry. They just take like the more expensive metal or the less reactive metal and they plate it with something. So electrolytic cell, electroplating, we'll talk about that for the next topic. It requires electrical current or energy or a battery. It's going to need some sort of energy in order for the reaction to occur. Within it, since you need some sort of electrical energy, it's going to be non-spontaneous. So this reaction will not happen unless you have a battery. Non-spontaneous means you need something else. You need something else to make the reaction occur. If you don't have the battery, you don't have electrical energy, this reaction will not occur. But we'll talk about that at a later date. For electrochemical cells, some key terminology you should be aware of is going to be the electrode. And my little post-it there electrode. I had electrodes. I had copper, I had zinc, I had magnesium, I had lead. So that pink Post-it, I labeled those things. It could literally be any metal. Electrode is a site of where oxidation or reduction will occur. Electrode is a site in which oxidation or reduction will occur. Let me finish off this little section right here. The electrode at which oxidation occurs is going to be the anode. It's called an anode. You saw anode earlier throughout the year. And the other one, the site where reduction occurs, is going to be called the cathode. And I'll give you a corny phrase to help you memorize anode, cathode, Leo, Ger. Last bullet, the site of reduction is going to be called the cathode. Red cat. Cathode. And that's where we'll call quits for today's class. All right, guys, once you're all set with that last section of notes, I'm going to stop there. We'll definitely elaborate. We'll figure out a lot more about voltaic cells. We'll definitely draw a voltaic cell. We'll go through and do that a couple times within this topic. But again, that's it for today. Please do not forget the half reactions exit passes due this Saturday. Please do that. That will probably be the only assignment due this week. So that's it for today, guys. Have a great day. Make good decisions. Hopefully you enjoyed how to make a voltaic cell with Mr. Brown today. We'll see you guys tomorrow. Have a good one. Voltaic cells. Bye, guys. See you, John. Bye, Nadina. Have a good day. Hopefully. Bye, Kim. Have a good day.